Hi students, let's look at this question here, which was taken from the textbook of AS Mathematics, Barry J. Harper Collins 2000. This was taken from the exercise 24, page 1, question 6. So it is modified. I believe this was taken from the ACJC tutorial. Let's see if I can do this proficiently. So now you're given that a rocket was launched at a fireworks display at time t. So this is time t here. The position of the rocket in meters relative to the launch pad O was given by this. Now, this position here is governed by the parameter t. So at t equals to 0, you can actually put into this equation here and find what is the position of the rocket. Okay, this is actually its coordinate system where it's only the horizontal and vertical unit vectors, right? So let me just explain here a bit. So if you have got these two axes here, so this would be your J. This is the vertical and this is the horizontal. Okay, that's pretty okay. Then how do we make sense of this? So let me just use Desmos calculator to show you how it looks like. I'm going to just use parametric equation, something which most of us because it's a parametric, right? This is essentially a parametric equation here where this R here can be expressed as R equals to 20t, and this is t minus 4 cubed plus 64. Right? So I'm going to just put this as 20t, 20t, comma, t minus 4 square, cube plus 64. Essentially just parametric equation here. So if I am going to this time t, right? So you just put this here. Okay. So when at you just switch it off here. So when time equals to 0, it will the starting point will be 0. So when we substitute 0 in, it will be 0, 0. Then when we move to 1.5 seconds, 1 second, it will just trace it out, right? So just go up 10 seconds and so on. So you can see that actually this path, it looks like this cubic expression here, which is true. Later we'll talk about that. So if you look at this, I'm going to put this as 10. You trace out the location is like that, okay? So essentially this is just a parametric equation. Okay, right now the height of the rocket when it exploded at t equals to 4. Okay, so just take note, the height would correspond to this. This is the vertical height. This is horizontal, right? So the height would be at t equals to 4. Okay, I just write down height is actually height at time t. Okay, is actually just t minus 4 cubed plus 64. This is the governing equation there. So at time t, height would just be 4 minus, actually just 0, right? You just substitute 4 inside. 4 minus 4 cubed. So it is 64 meters. Okay, that's pretty okay. Now then, after which we want to find the displacement of the rocket when t is 3 and t is 4. So displacement is essentially final position, final minus initial, right? This is what we learned in secondary school. So displacement will be final S2 minus S. So S4 minus S3 then. Okay, so the displacement at the position at 4 minus off the position at when it's time equals to 3. I think it's not really an issue there. So when time equals, just use this governing equation here. So time equals to 4 and 3. So in this case here, when S equals to 4, I'm going to substitute this into here, 20 times 4. So there will be 20 times 4. 4 minus, so this is 64 minus of 20 times 3. 3 minus 4 cubed plus 64. Okay, so I'm just going to do this. This is 80, 64, and this is 60, and that will be 63. Okay, then in the end, what I'll get is actually 20 and 1. So this is the displacement here. That's the displacement of the rocket between t equals to 4 and t equals to 3. So we can write this in this form here, not an issue. Okay, or just leave it in this form is fine. Okay, column vector is fine. Now let's look at part 3. Show that the Cartesian equation was this one and sketch the path of the rocket, hence state the direction of movement of the rocket when it exploded. So part 3 is here. Okay. we have from this case here, so I'm going to just use this here. Okay, from this case here, what we have is actually x equals to 20t and y equals to t minus 4 cubed plus 64. Right? Now, Cartesian form just means that we get rid of the parameter. So in this case here, to get rid of parameter is pretty okay. What you do is just make t the subject here. So t, get rid of the parameter here. So I'm going to make t the subject. So t is just x over 20. So I'm going to sub 1 into 2. Okay. So this case here, what we get is y equals to x over 20 minus 4 cubed plus 64. Pretty straightforward there. Get the expression, the Cartesian form. So this is a Cartesian form. Cartesian equation. Okay. Now, sketch the path of the rocket. So when you sketch this path, this is a cubic expression. So you know that this cubic expression here, it has a general form of this. So it looks like that and go up. Okay. So this is a cubic. So there's a point of stationary point of inflection in the middle here. But you can actually use your graphing calculator to actually deduce this graph here. So let me show you how. So from here, what we do is we just need to key in x over 20 minus 4 to the power of 3, and we're going to put this as plus 64. Okay, now if you were to zoom standard, obviously you're not going to see anything because you should know that this is a cubic equation. So you could just use zoom fit if you want to, or you can just zoom out. Okay, I'm going to try and just zoom fit. Zoom fit meaning you will see some of the general shape there. So I can't really see that. What I can do is just go to Windows settings and change. But anyway, time has to start from 0. So I'm probably going to put like 30 here. Then this probably put 0, and I'm going to put this as 100. Okay, not sure. Oh, it's not showing. But this curve here, let me see if we can put this as 100. There you go. Okay, it's slowly showing the shape there. So if we're going to do, there you go. This is the curve that you're looking at. So this is 150, maybe it works. Okay, great. So this is the graph here. Okay, this is a stationary point of inflection, very important. Then window, maybe Y max. I'm just going to put this as 150. Okay, so I'm just adjusting so that I would see the shape that I want to see, which is a cubic expression there. So this is how it looks like. We're going to do Y, and this is X over here. Just know that this would be 0. Okay. This is the Cartesian equation. The timestamp is not shown on this graph, so please take note of that. Sketch the path. So I've already sketched the path here. Show and sketch. Hints at the direction of movement in the rocket when it exploded. So we need to find where does it explode. This is when t is equals to 4. Okay, so when t equals to 4, at t equals to 4, y is actually 64, right? This is actually y value. So at t equals to 4, y is equals to 64. Okay, so what we can do is actually just t equals to 4, x will just be very simply put it 20 times 4, which is 80. 80 times 20 times 4. Just 20 times 4. Okay, 20 times 4 here, which is 80. So you need to see where is it on the graph here. You can actually just trace and just put 80. You get this point here, 80, 46, 64. Okay, anyway, this point here, point of inflection, would be when this is 0, so when this is 0, this point of inflection here, when you let this be 0, this is when x 20 minus 4 equals to 0, x equals to 80, and this is y equals to 64. Okay, so everything will point towards the stationary point of inflection here, which is actually 80, 64. This is the stationary point of inflection. This is when t equals to 4. The stationary point of inflection. So if this is a stationary point of inflection, what you can tell that when it explodes here, it's just going to go this direction. You just go horizontally, right? So this case here, what we can write down is when it explodes here, you will just hence the direction of move rocket when exploded. Direction of rocket and explode direction will be horizontal and towards the positive x-axis. Okay, positive x direction. Okay, that is the direction will be 1 0. That is 1 0, meaning you're pointing towards this direction here is 1 0. Just pointing towards this direction here. Okay, that is just eyeing. Okay, so that's how I do this question here proficiently. If you have any questions at all, please let us know, and I will see you in the next question.